Welcome to section 15.9. Okay, gentle people, one of the things that you might recall is one of the factors that increases the rate of reaction is something called a catalyst. So a catalyst is something that can speed up a reaction, but what's key about a catalyst is it itself doesn't get chewed away, it doesn't get used up. So it is not consumed, it's there at the start of the reaction, and after you're done with the reaction, you still have your catalyst remaining. So remember, when we are talking about kinetics, kinetics is all about the pathway. And so the way the catalyst speeds up a reaction is it gives us another pathway to go through. And so the idea is if you have an uncatalyzed pathway, you have a certain activation energy. Now, a catalyzed pathway gives you a different path, and if it gives you a different path, there's a new activation energy associated with that. And that new activation energy, if it's lower than the previous activation energy or the uncatalyzed activation energy, that means that your reaction will proceed faster. So let's go ahead and remember my analogy. Let's say that you are at point A and you want to get to point B, and you have to overcome some mountain or some threshold to get from A to B. The idea with the catalyst is instead of going over the mountain, you guys have a little tunnel that is halfway up the mountain that lets you go through it so that you can avoid going through the summit and then coming back down. So it's easier to get from A to B, or in other words, it is faster to go from A to B. So one of the unfortunate things about doing an online class is I don't get to show you demos in person. So what I'm going to try to do is link to a YouTube video right now. You guys can go through a YouTube hole and watch all the videos. This is a pretty popular demo that I usually do in front of everyone, but go ahead and watch that and we'll talk about that video in a second. Okay, gentle people, I hoped you enjoyed that little campy video, and so let's go ahead and break that reaction down in terms of chemical equations. So what you guys saw was hydrogen peroxide, and hydrogen peroxide, as that gentleman mentioned, is something that naturally decomposes. So you guys can go into the store, buy those brown bottles of hydrogen peroxide, and what you will notice is that after a while, when you take that hydrogen peroxide home, it goes bad. And that's because it decomposes really slowly into water and oxygen gas. Now, what that video showed you is that instead of this process taking months, we can do this reaction and decompose all of it within a few seconds. And so what that gentleman added was he added iodide. So I minus right here. And this is going to be our catalyst. So let's go ahead and see what the reaction is. So we have hydrogen peroxide. It's going to be combined with iodide. And what you guys are going to make is you are going to make this hypoiodite and an equivalent of water. And then what's going to happen is you guys are going to take that hypoiodite and you guys are going to go ahead and combine it with H2O2, another thing of hydrogen peroxide, make water, and then oxygen gas right here. And so if we take a look at this, we can see the fate of all our chemicals. What you'll notice is I minus is first consumed in that reaction, the first step of my reaction, and then it is reproduced in the second step. And so this is why it is a catalyst. It gets eaten first, and then it gets reproduced. And so at the end of the day, the catalyst is not consumed itself. Now, this differs from what an intermediate is. You can see that my hypoiodite right here is first produced, and then it is consumed in the second reaction. And so there is no hypoiodite in the overall reaction. Now, if we go ahead and cross these things out, you can see that I get my overall reaction when I add those two reactions up together. And so this is what a catalyst is. It speeds up the reaction by giving it a different path, but ultimately, if it is consumed in one step, it'll be regenerated in a subsequent step such that it is not consumed overall. Now, if you were paying attention to that video, he actually mentioned something called catalase. Now, catalase is actually an enzyme in your body. And what an enzyme is this is a protein, but more specifically, this is a protein that is a biocatalyst. And so the question becomes is why would you need a biocatalyst in your body? Well, it turns out that anything that breathes oxygen, you have a metabolism that consumes oxygen, and sometimes there are side reactions, sometimes there are mistakes that have been made. And so what you make are these reactive oxygen species, so ROSs. And so these things are pretty bad for you. So things like hydrogen peroxide, if they get into your body or if there's a whole bunch of it, this chemical has the potential to screw around with your DNA. It breaks cell walls. It is something that biology doesn't want to have around. It's a very good disinfectant. Now, you are going to naturally make a little bit of hydrogen peroxide by mistake or side reactions, so your body has to take care of this. Now, these ROSs like hydrogen peroxide, we need to say that these are deleterious oxidants. So you might have heard people say, oh, you should eat these because these are antioxidants. And what they're saying is you should eat something that combats these ROSs. But I'm going to tell you guys, you naturally have a lot of these in your bodies, and this is one of the things that scientist mentioned. So catalase is an enzyme inside your body, that biocatalyst that takes care of hydrogen peroxide. And just to give you an idea how good an antioxidant this is and how good at its job of destroying hydrogen peroxide it is, let's take a look at what we saw before. So we had hydrogen peroxide, and we saw that we added a catalyst to go ahead and make oxygen and water. Now, in the videos and in my slide, I mentioned I-. A comparable catalyst here is iron 3+. So if you took a rusty nail and chucked it inside one of those bottles of hydrogen peroxide, you decompose that hydrogen peroxide pretty fast. Now, the problem is you don't want rusty nails floating around your body. You don't want iron 3+ floating around your body. That would lead to some other bad stuff like you getting tetanus shots and all of that. So what your body did is your body came up with this enzyme where it took this iron 3+ and actually put it inside this protein. And so what I want you guys to notice is each one of these little blobbies or blips that you see in this picture is an atom. So this protein is made out of thousands and thousands of atoms. And right here with this white line, you guys can see is an iron 3+. So that's my catalytic center. And then the rest of this protein is to keep the iron from floating away, but it's also to help make that catalyst a better catalyst. So if you guys were to look at iron 3+ as a catalyst, it increases that rate of reaction by 30,000. Now, your body has finely tuned this catalyst, and in this case, catalase, this enzyme with iron 3+ in it, well, it increases the reaction 100 million-fold. So this is an excellent catalyst at taking hydrogen peroxide and making it into oxygen water. It's there to protect you from this reactive oxygen species. Now, speeding up all reactions isn't always a good thing. So one of the things I want to talk to you guys about is the work by Roland and Molina, and they were working at our sister school, UC Irvine. And so what they are atmospheric chemists, and they were looking at these compounds called chlorofluorocarbon. Now, chlorofluorocarbons was heralded as a great chemical. So what it is used for, it is used for refrigerants and as propellants. And previously, people were using things like ammonia and SO2, and these things were horrendous if you got a leak in your refrigerator or your air conditioner. These were toxic gases. And so when people found this gas, in this particular case, this chlorofluorocarbon, people loved it because this is something that was non-reactive. It wasn't poisonous. So if something sprung a leak, it wasn't going to damage or hurt people. Now, this molecule is highly unreactive. And so people thought this is a great chemical, but there's something kind of interesting in what happened. So you see, if I wanted to draw the Lewis dot structure of this, it would look something like this. And what happened is it was so unreactive that this chlorofluorocarbon escaped, and then it went into the atmosphere. Nothing reacted with it until it hits the upper atmosphere. And when it hit the other atmosphere, there was UV radiation. And this is high energy electromagnetic radiation. And this radiation had the power to start breaking bonds. And more specifically, when it broke bonds, it did something what's called a homolytic cleavage. So that means when it breaks the bond, it breaks it evenly such that there is one lone electron on one side and one lone electron on the other side. Now, we haven't talked too much about a lone electron. We've talked about lone pairs, but this isn't a paired electron. Now, when you have a lone electron, this is a highly reactive species, and it is referred to as a free radical. So what Rowland and Molina said is that our CFCs, they went into the upper atmosphere and they generated these free radicals. Now, this is what they got the Nobel Prize for. Now, if you're an atmospheric chemist, what you guys would know is that O3 is going to react with atomic oxygen in our atmosphere, and it is going to make O2. So that means ozone naturally gets depleted, but there's mechanisms where it gets regenerated in our atmosphere. Now, this reaction that I'm showing you guys right here is a very slow reaction, relatively speaking. So what happens with that free radical that I generated on that last slide? Well, that free radical can react with ozone, and that's going to make an O2, and it's going to make this intermediate right here. Now, that intermediate is going to go ahead and react with my atomic oxygen, and when it reacts with my atomic oxygen, what you guys will see is I regenerate that free radical again. And so, again, to show you guys, I first consume something, and then I regenerate it. So this free radical is acting like a catalyst. And so what happens is when these free radicals get generated, it speeds up that reaction. In fact, it is estimated that one of these molecules right here, one free radical, is responsible for destroying 100,000 O3 molecules before it reacts with something else. And so this was the problem that the world was facing, that we were slowly depleting our ozone layer by using these gases in our refrigerants, our air conditioners, and our propellants. And so this spawned upon what's called the Montreal Protocol. Now, if you are an environmental scientist or interested in public policy, the Montreal Protocol is probably one of the most successful environmental policies. What happened was the world banded together and agreed and signed a treaty that they would try to stop using these CFCs, these things that generate these chlorine radicals, in order to protect the ozone layer. And you can kind of see the fruition of this policy because our ozone layer is starting to grow back, and so this environmental policy is starting to work. It is estimated that all the damage humans have caused is supposed to be repaired by the year 2040. And so we are fingers crossed hoping that that happens. But what I really want to show you guys is here's a catalyst. And again, catalysts speed up reactions. You might not necessarily want to speed up certain reactions. All right, let's take a look at some of the reactions that inspired those Nobel laureates to do their work. What we know is nitric oxide is a gas that goes ahead and reacts with ozone. Go ahead and tell me in this reaction mechanism what is acting as a catalyst and what is my intermediate. Okay, gentle people, let's go ahead and take a look at what happens. So in the first reaction, we see that NO is consumed, and then in the second step, it is reproduced. So if that's the case, if it's consumed and then reproduced, that means it's a catalyst. Now, NO2, on the other hand, it is going to be produced, and then my NO2 is then consumed. So if it is produced and consumed, that means that NO2 is an intermediate. So at the end of the day, if you run this reaction, you should not have any NO2, but you should start with the original amount of NO you had before you started this reaction. So if we were to talk about catalysts, they usually come in two types or two flavors: a homogeneous catalyst and a heterogeneous catalyst. Now, these qualifiers pertain to the physical state the catalyst is in with respect to the reaction it is trying to catalyze. So a homogeneous catalyst means that it's present in the same phase. So if you have a reaction that is aqueous, your catalyst is going to be aqueous as well. Now, the advantages of a homogeneous catalyst is it's easier to understand the mechanism it goes through. So you can vary the catalyst, you can change concentrations, you can go under pseudo first order, all this a bit. And so that means you have a deep understanding of the catalyst, which means that you can improve on the catalyst by making it more selective, only doing certain types of reactions, or only going at a certain speed. So these catalysts are very tunable. It also turns out that these catalysts require milder conditions. You're not going to have to boil things. You're not going to have to worry about heat transfers as well. These catalysts don't get hot. They're relatively mild compared to other reactions. Now, the homogeneous catalyst is a catalyst that is in a different phase. So the idea here is if you had an aqueous reaction, you can have your catalyst that is stuck on this solid piece of material. You can stick that solid in, it catalyzes the reaction, and then you can pull that catalyst out. Now, the benefit to this is it's easier to recover. And this is a big deal when you're talking about industrial processes. If you're a homogeneous catalyst, you got to figure out some way to separate your products and your reactants. But if you have a heterogeneous catalyst, all you can do is just filter your reaction after the reaction's complete, and you can recover your catalyst and use it for your next batch of reactions. So let's go ahead and talk about a heterogeneous catalyst, and that is one that kind of has an interesting backstory. So this reaction, N2 combined with 3 hydrogens to get you to ammonia, is a very slow reaction. You can't produce a lot of ammonia this way. Now, ammonia is a prominent component in explosives. And so during World War I, what happened are the Allies controlled Chile, which was the biggest source of ammonia at the time. And so if you controlled the ammonia source, you controlled how many bombs you can make. And so 2 German scientists, which were blocked, or Germany was blocked from Chile, were trying to figure out how they can make more bombs. And so these 2 German scientists, Haber and Bosch, came together and figured out a way to make ammonia. Now, they used iron parts and an iron solid catalyst, and if it wasn't for them, one could say that World War I would have ended really, really quick because Germany would have been outgunned. Now, what's really interesting about this story is if it wasn't for them discovering this process, most of the world would probably starve. And that's because ammonia is a key component in making fertilizer. So this reaction, while it was first figured out or first catalyzed to make bombs, is actually a reaction that if we didn't have, we wouldn't be able to feed the world's population. So let's go ahead and talk about how this catalyst works. So what happens is you will have nitrogen. So this is going to be our N2 molecule, and it has a triple bond. Now this triple bond is super strong to break. So what happens is the nitrogen is introduced to a metal catalyst. And so that metal catalyst gives an alternate pathway for this reaction to occur. What's going to happen is that nitrogen is going to go ahead and sit on that iron catalyst. And so this is called an adsorption process. And what's going to happen is that iron is going to do a reaction. It's going to break those bonds. Now, once it breaks those bonds, what can happen is our hydrogen is going to come over and start reacting. And I'm going to put 1, 2, and then 3 hydrogens on there. And once I've got my 3 hydrogens on there, it no longer wants to stick to the iron. And so my ammonia is going to go ahead and deabsorb from the surface. And so the steps in this process is first I have an absorption. So that means nitrogen sticks onto my catalyst. The catalyst then breaks the bonds. And once the catalyst breaks the bonds, then my hydrogen comes and I form new bonds. Once all the bonds are formed, I go ahead and deabsorb or regenerate my catalyst surface for a new nitrogen to come and sit on there. Now, these heterogeneous catalysts are really interesting. So if you remember the eye clicker question, one of the things that I showed you was NO. And it goes ahead and it depletes the ozone. Another thing is N2O comes and depletes ozone molecules as well. And N2O is a byproduct of your combustion engine in your car. So what we have to do is we have to take care of N2O before it reaches the atmosphere, before it actually goes ahead and exit your exhaust pipe. Now, you might have heard about this part in your car. This is what's called your catalytic converter. And your catalytic converter is a heterogeneous catalyst. And so what happens is you have a surface, and that surface is made out of rhodium metal. And what happens is we have N2O, and it goes ahead and absorbs onto that rhodium, and then it goes ahead and breaks that N2O into nitrogen and oxygen, 2 things that are safe for our atmosphere. So this again kind of works exactly like that last process that I showed you. But what's interesting about these heterogeneous catalysts is that these things make reactions 0 order. So if you guys take a look at this, what you will note is if we did the chemical kinetics of this, N2O is 0 order. And that means the concentration of N2O does not matter. And the reason it doesn't matter is if you remember the process that I described. For this reaction to be catalyzed, I have to have my molecules absorb onto the surface. Now, there's only so much surface. Once I fill up the surface, no other new molecules can go ahead and proceed with this reaction. So the concentration of my gas doesn't matter because the surface is already filled. Now, what I can do is if I increase the surface or the amount of catalyst, I can speed up this reaction. And this is why I'm showing you guys this cutaway of your catalytic converter. what you guys will see is your catalytic converter kind of looks like a honeycomb. And that's because we want to try to get as much of the surface area, as much of that rhodium exposed to the atmosphere so it can go ahead and can do this conversion and convert your N2O to nitrogen and oxygen. Kind of a cute little aside is this rhodium catalyst is a very expensive metal. It is more expensive than gold, and this is part of the reason why people like to steal your catalytic converter, because it's probably one of the most expensive small parts in your car. Well, I hope that made sense, gentle people, and remember to stay safe.